Hello, I'm Henderson, a PhD student in astronomy at The Ohio State University. Today I'll be telling you about my recent paper titled Optimal Survey Strategies and Predicted Planet Yields for the Korean Microlensing Telescope Network, on which I have worked with my PhD advisor, Dr. Scott Gowdy, Dr. Chung-Go Han of Chungbuk National University, and several other collaborators. Gravitational microlensing occurs when the light from a background star is lensed by the gravitational field of a foreground mass or system of masses. The magnification of the background source provides a tool with which it is possible to search for planets around stars that are faint and/or distant. The microlensing technique is intrinsically sensitive to planets on orbits of a few AU and can probe down to very low-mass planets, making it a required complement to our present array of planet detection methods, without which it is currently impossible to obtain a complete picture of exoplanet demographics. The Korean Microlensing Telescope Network, or KMTNet, is a network of 3 survey telescopes that will be dedicated to monitoring the galactic bulge to search for exoplanets via gravitational microlensing. In this paper, we present the results of simulations that optimize the observing strategy for KMTNet and predict the planetary detection rates that KMTNet will obtain. KMTNet is a network of 3 telescopes, each with a 1.6 meter aperture and a 4 square degree field of view. Figure 2 shows the locations of the observatories and their planned chronology, with the first being installed at CTIO in Chile, the second at SAAO in South Africa, and the third at SSO in Australia. KMTNet will provide near-complete longitudinal coverage and some nearly continuous observations of the galactic bulge for the microlensing observing season, from early February through early November, and will obtain deeper photometry at a higher cadence than current microlensing survey telescopes. Our KMTNet simulations consist of 4 primary components. First, we generate a population of lens and source stars drawn from a galactic model that matches empirical constraints. Then, we compute parameters for binary microlensing events. For each of these microlensing events, we calculate magnification as a function of time and simulate realistic observing conditions and effects, ultimately computing an observed light curve. Finally, we subject these simulated light curves to a series of detection criteria. Figure 10 shows an example detection of an Earth-mass planet on a 1 AU orbit. Planets can be robustly detected in events with even shorter timescales, lower amplitudes, and fainter source stars. We use our simulations to optimize the locations and number of the target fields, as well as the exposure time. In considering non-overlapping fields that avoid regions of high extinction but are constrained to our dust map, we do not find a clearly optimal choice of field locations for the 5 tilings we investigated. We thus use empirical microlensing measurements of the microlensing event rate to select a preferred tiling of target fields, shown here in Figure 13, overlaid on our extinction map. We furthermore find slight preferences for 4 target fields and an exposure time of 120 seconds, leading to a 10-minute cadence given the 30-second overhead time for KMTNet. Using these observational parameters, we then compute the expected planet detection rates for KMTNet. Figure 17 shows the predicted planet detection rates as a function of semi-major axis for different color-coded planet masses. The rates peak at a semi-major axis of a few AU and drop off more steeply towards smaller separations, which is what we would naturally expect for microlensing detections. Figure 18 shows the predicted planet detection rates as a function of planet mass using 2 different normalizations. The solid black line assumes 1 planet per deck squared in planet mass and semi-major axis, while the dashed line assumes a version of the Kazan 2012 cool planet mass function that we have saturated at 5 Earth masses. We see that the latter normalization predicts detection rates that are roughly uniform in log planet mass across a wide range before steeply declining for smaller planet masses. Using this, we predict that KMTNet will detect approximately 65 total planets per year across the ranges we explore. In Figure 29, we show planet mass as a function of semi-major axis for all known planets and overplot our predictions for the detection rates KMTNet will obtain, including those for free-floating planets, or FFPs. We thus predict that KMTNet will significantly augment the number of known exoplanets near and beyond the snow lines of their host stars, facilitating synoptic studies of exoplanet demographics across an unprecedented range in both planet mass and semi-major axis. In order to facilitate visualization of and improve intuition about the planetary systems that we predict KMTNet will detect, we also present a large-scale online atlas of light curves, which we describe in our second appendix, and an example of which is shown in Figure 31. In each figure, of which we have created thousands across our full range of planet mass and semi-major axis, we show the full light curve, the planetary perturbation and its residuals, the caustic geometry, and the parameters. To view this light curve atlas, please visit the following website. To conclude, we present the results of simulations that optimize the observing strategy for and predict the planet detection rates of KMTNet, a new network of telescopes to be dedicated to monitoring the galactic bulge in order to detect exoplanets via gravitational microlensing. We predict that KMTNet will significantly increase the number of known exoplanets, particularly at separations of a few AU, and will thus facilitate the first synoptic studies of exoplanet demographics across such a wide range of planet mass and semi-major axis. Thank you very much for listening, and have a great day.